Hello, this is Junichiro Horikawa, and today I would like to try to implement this Physarum simulations introduced by a Sage Jenson, as well as the paper by Jeff Jones called Characteristic of Patterns, Formation, Evolution, and Approximation of Physarum Transport Networks. Now, this artist called Sage Jenson has explained a brief description about this paper in really easy to understand sketch right here. So what I'm going to do today is to try to follow this sketch to create this kind of really interesting simulation, which is a simulating a trail of slime mold to create this kind of really interesting simulation and try to implement that in Houdini today. Okay, so let's see how I should get started. Now it says that, it says that there are two types of datas. One is the agent-based layer data, and one is the continuum-based layer, which is the trail map. And the data map consists of many particles. So the first layer, I guess this one, data map, consists of many particles, and I guess those particles are the base of the slime mold. And while the trail map consists of a 2D grid of intensities, so which is this one. So when it says 2D grid, I guess it means as like an image, what it says here is similar to a pixel-based image. The data and trail map in turn affect each other. The particles of the data map deposit materials onto the trail map, while those same particles sense values from the trail map in order to determine aspects in the locomotion. So there's kind of a feedback loop in between those data map and the trail map. The data map, each particle deposit this kind of pheromone-like object into a trail to create a trail and each time frame, and also this particle is also referring to those pheromones which other particles have deposited it previously to determine which direction this particle should go in the next frame. And it says right here, each particle in the simulation has a reading heading, angle, a location, and 3 sensors, which I guess is this one. Front, left, front, right. The sensor reading affects the heading of the particle, causing it to rotate left or right. And the trail map and the goals, the diffusion and decay process, every simulation steps. So the particle, I guess this one, has 3 sensors, left, front, and right, and based on the value strengths which those particles have sensed from the trail map, it seems to change its direction. If the sensor on the right hand side found the most greatest, then turn right. If it's on the left, turn left. If left one and the right one is bigger than the center one, then just go randomly left or right. If the front side sensor sensed the bigger value, then just go straight. So something like that, and after rotating, move to that direction and deposit this pheromone onto the trail map and do a diffusion. In this case, I think it's a 3x3 mini filter, so it's just a smoothing or blurring. Then decay, so the pheromone, the value of the pheromone will decrease on each frame at some ratio, I guess. And go back to the sensing. So sounds straightforward, pretty straightforward. What we just need to provide is 2 layers of data, the particles on trail first, and I guess since this is the grid image, we could either use a 2D grid like a plane or volume, and for particles we can just use create with points. And I guess using volume makes sense because it gives you a bit more faster calculations when we use volume wrangle. So let's try to use volume together with the point to actually simulate this thing. Okay, and here is kind of a result that we're going to create today. And as a result, we'll be able to create this kind of interesting pattern being created on top of the volume using a particle running on top of this plane or this volume. And you can actually see this particle running like this. Right, so let's try to do this. Let's try to simulate this from scratch. Okay, now let me open up the Houdini. Okay, let me save this file so that I don't lose the process. I'm gonna make Physarum. Now let's start from making a geometry node. Then first of all, I'm going to create some basic grid as a base size to determine the base size. So let me also show the wireframe as well. Now, and let's also have some parameters so that we can control some of the parameters that we want to control. So first thing I would like to control is the size of this grid. And this size is going to be used as the resolution as well. So I always want to make 1 pixel of the image as 1 in this case, so that it'll be easier to control for myself. Okay, so I'm going to set the width and height the same, and let's just name this as res, and set the resolutions from 0 to say 1000. Okay, and let's say accept, and let's set the default to be around like 200 maybe. Copy this and paste it to this size here for the y and x and y. Okay, and the rows and columns I'm gonna keep it as 2. Okay, so you have this big plane which the width is 200, the height is 200. Alright. Now what I'm going to do next is to create a base for the particles on top of this plane. So let's create a scatter node for this plane, and you need to define a number of particles here. And I saw in a different blog post talking about the Sage Jenson same algorithm, saying that using the same number of particles, using the pixel, multiplying the pixel for the width and height will be the best number for the number of particles. So in this case, the width is 200 and height is 200, so 200 by 200 will be the best number for the particle. So let's try that out, but might going to be really big if the resolution become like 1000, then you have like millions of points. So you might also need some limitation what's the maximum number for the points. So first of all, I'm going to paste this resolutions here as an expression for the force total count and use power by 2 to multiply 200 by 200. I also want to create some parameters for the points to set the limitation. So max particle num, max particle num, and let's say the maximum will be like 50,000, or no, 500,000. 500,000 to be the maximum. Might be too big. I might need to change this later on, but let's set it as it is for now. And let's say the maximum for now is 100,000, so or 200,000. Okay, and let's copy this here, and I'm going to use min function for the expression with this maximum value, so that I will choose either the minimum either this one or the 200,000 points. Okay, so for each of the points I need some attributes which is related to the values that's going to be used in order to check, in order to sense the trail map, and also where it's going to go. So first, the information that we need is this angle here, sensor angle and sensor distance here. And also we need to give a velocity value in order to determine where to move, in which direction it should move. In that case, we need to also define the amount of the movement, I guess. The location is already defined by the p value, p attribute, so that's fine. So I guess those are the information we need. Let's try to give those as an attribute to each of the point. Okay, so I'm going to give a point wrangle. Let's set init. And first of all, velocity, which is going to be used as the heading direction. So I'm going to just use no random direction for now, and subtract by 0.0, 0.0, 0.0, and normalize this so that the direction goes everywhere 360 degrees. Now, since we are dealing with the 2D plane here, we can ignore the y value. So let's reset to 0. And in this case, we might want to normalize this again. So I guess I don't need to normalize it here. So normalize v at L. Okay, let's see how it looks like. So velocity, yeah. So these are the initial heading direction, which should be random value. Okay, now let's also set a search distance as a float value. So sdist is equal to, let's give a parameter for this one, search distance. And what else? We also need a search angle. So I'm gonna say sang chf search ang. What else? When it turns right or left, I guess we need to define the rotation angle, I guess. Yeah, right here. So let's give the rotation angle as an attribute as well. So f at rotation angle, chf rotate ang. And what else? We also need to define how much it moves in each frame. So f at move distance, chf move dist. Okay. I guess that's pretty much it for now that we can set the position. Right, so let's do like this. It also says that the position amount right here. Maybe we can also define that as well, or maybe later. Let's see. So, well, each particle might have different values. It might have different position values, so it does make sense to have each particle have this attribute. Okay, so other one is a bit more related to the global, so I think it's fine. The sensor size, okay, well, the sensor size I guess is used to define the size here for the square, to how much it reads the nearby points. Well, for now I guess I could say I could just use like a single point to search for the single trail datas, but it does might make sense to make a data size. Okay, so let's have this as an attribute as well. So going back, f at the amount, deposit amount. For now I'm going to use the static values for these, so every values for each particle will going to be the same, but I might want to change those differently later on. So for the search distance, let's say, I'm not sure what's the best value for this one, but currently the single pixel is the distance of 1, so consider that. I will going to set some values here. So search distance to 1, move distance to 1, search distance to 3, search distance, move distance to 1, and search angle I'm going to set it as a degree, so let's say 30 degrees, and for the rotation let's say 15, and deposit amount say 0.01. Okay, now let's have all these parameters as a global parameter here inside a node controller here. So I'm going to create a separator first, then set uncheck for bit linking parameters, then drag and drop these stuff one by one. Okay. Now what else? Search distance, we need to set the range here. So the search distance, I'm gonna set it from 0 to 10. For the search angle, I'm going to set from 0 to say 90. This one is same. And move distance from 0 to 10, and the deposit amount from 0 to like 0.1 for now. And we also need some decay factor as well, so let's also have that decay factor. For that, I'm going to set it at 0.0.1 as well. We might also want to apply a sensor size, which is written here. Sensor size here. There is also a deposit size as well. And the diffuse size, I guess I will just keep this as a 3 by 3 means, so I'm not going to change this one. So for the deposits, well, deposit size is also, it's going to be a bit more hard to control, so, and also for the sensor size. So I'm just going to leave it as it is for now to check for the single point, and later on if I have more time, then I'll try to implement those sizes as well. Okay, so for now these are the essential values needed for the particles. Okay, and let's also apply some groups to this point. Just going to group node. Just going to use a group node to set as particle. So group name particle for the point. Okay, so the point become particle. Now I'm also going to set a number of, I'm going to also count the number of points currently inside a node, later on I'm going to use that to use volume wrangle to control the point direction or the movement. I'm not going to split the function for the point wrangle and volume for the volume wrangle, but actually I'm going to use single volume wrangle to control all the values, both for the points and both trail map, which is going to be the volume. The reason is because by doing it you'll be able to calculate the process really fast, since you don't need to split the calculations into two different nodes. Okay, so to do that we need to have an information how much points are there. So I'm going to create a attribute wrangle. Let's set it as a detail init and set it as detail, and create the attribute for integer named as numPoints, and set the number of points in this current node. So currently I have, I think, 40,000 points. Okay, now that's enough for the particles. Let's also create a grid information for the trail map with a volume. So to do that, first I'm going to connect the volume node to this plane, and currently the resolution is 10 by 10, so I want to make the resolution same as the width and height, so let's using this value. So copy this one and paste it right here to the uniform sampling divs, so that you'll be able to control the resolution like this. Now since I'm going to merge those points and volumes together, I need to be able to make some differences between them with the group. So I'm going to make a group first for the primitive. I'm going to name it as map, and just in case I'm going to create a point group as well for this volume, using the same name, map. Okay, let's look at this in a geometry spreadsheet. So I have primitive with a map group, also point as a group map. Right. Now let's merge these together. And also I forgot to name this volume, since the deposited value is going to be called as pheromone here. I think it was called as pheromone. No, not in this paper, not at this page, but I'm gonna call those white stuff seen in the trail map as a pheromone, which will attract the particle to go forward to. So I'm gonna name this density value for the volume as pheromone. Okay, so pheromone. Right. Now the initial value is 0, but that's fine. Okay, so in terms of setup, I think that's fine. This is fine. Now I'm going to create a subsolver to actually calculate these simulations based on the sketch. Okay. Now, okay, going inside, and what I'm going to do is to just use volume wrangle to calculate both a trail map and a point. Okay, so the timing might be a bit weird if you write it on everything in one, but since it's going to be iteratively rerun on every frame, on each frame, so I think it's not that big problem. Now I also need to think about the particles, when the particles go outside the boundary, how we should treat with those particles. In this case, it seems to me from what I see in the pictures or the screenshots for this artist from this artist Sage Jenson. Seems the particles which has gone outside the boundary goes in again from the other side. So if you go to the left side, it will come back to from the right side. So I would like to create that kind of same behavior to this particle. If the particles go out on the left side, coming in from the right side. Okay, to do that we need to have some kind of information for this boundary, right? And I think you can get this boundary information by accessing to the boundary of this object. Yeah, and I think it shouldn't take much time to calculate the boundary, but I'm actually going to use the bounding box functions in order to calculate the boundary, so I'll just leave it as it is. Okay, now I'm gonna calculate it as a calculation. Now let's open up the editor to write some values here. First, I'm going to bring up the pheromone value from the density of the volume. Okay, since this is a volume wrangle. Right. Now, first of all, I'm going to calculate the bounding box, minimum points of the bounding box and maximum points of the bounding box. I guess in this way. Okay, so that is, first of all, I'm going to create a min and max vector, empty vector, then use a function called get bbox from the first input, update the minimum maximum. Okay. Now also I'm going to retrieve the number of points from the detail. This. Okay. Now, the good thing about using the same number of the voxel resolutions and the number of points is that you can, for each voxel calculation, you can also calculate the points as well. And I also have limited the number of points at some limitation, but it is assured that the point never goes up or higher than the resolution of the volume. So within those rules, I can calculate both points and each of the voxel at the same time, which makes the calculation time a bit faster. Okay. But to do that, we need to try to create an ID value from a voxel index, which from IX, IY, and IZ. So these are the voxel index here for each voxel. And we need to convert this into a single value so that we can use this as a point number to access to a point. Okay. So to do that, first I'm going to name the index as ID, and we're going to calculate the index. And to do that, we can think like the voxel, like in 3D it looks like this. Like this, right? So at each voxel index, we are picking this current voxel right here. And we need to know the single index number at this point right here, and let's say this is the x direction, this is the z direction, and this is the y direction. Okay. In this case, we can determine this index by first of all multiplying the total x multiplied by z. So in this case, at res x multiplied by at res z, since this is the resolution number for the x direction and z direction. And also by multiplying it, you'll be able to get the 2D grid numbers first. Now then we can multiply this by a number of voxels on the height. Okay, let's call this y prime. So y prime, and in this case it is equal to a at I y. When it's 0, it's when it's 2, when the number is 2, then you have 0, let's say 0, 1, 2. When it's 0, you have no grid on 2D, but you have just the first layers. If it's 2, or if it's equal to 2, you have until here. And then you can, what you just need to do is to consider these up top values here. Okay, so the next thing you want to do is to add, in this case, a res x multiplied by in this case iz. Okay, so this is the number of iz here, which is equivalent to z prime. And then we are left out with this single voxel here, which can be an ix. So this calculation indicates the single index value for h voxels. Okay, so ix is equal to iz multiplied by ix plus iz multiplied by res x plus iy multiplied by res x multiplied by res z. Okay, so this will be the index value that you can use to determine for each point, which it can also be used for each point number. Okay, and next thing I like to do is to check if the ID is less than number of points, number of total points. Then we can start to use this ID as a point number to calculate the point position. So let's try to do that. First of all, let's get all the information that I need from the point attribute. So first of all, velocity, point 0, velocity d, and its distance, the search distance, point 0 vel, no, its distance id, float, search angle, point 0, search angle, id, float, rank, point 0, rank, id, that's the rotation angle, and we also need the position itself, so we can access to the point. What else? We could also get the moving distance, so float mdist, 0 and dist ID. Okay, I think we had deposit related stuff. Let me apply this and go back to see what was the name of the attribute. So that was a D amount. Okay, so going back, float the amount, 0.0 the amount ID. Okay, now next thing I would like to do is for each point I would like to create a sensor for 3 sensors, one for the forward, one for the left side, and one for the right side. Now the front side, it can be determined from this heading direction, which is this velocity value. So let's create a front side distancing vector from each of the point. Okay, so from this point I would like to use this heading direction with the size of this search distance. So let's create that kind of vector by saying vector FL front velocity is equal to, first of all, normalize the velocity, then multiply by search distance. Okay, now in order to get the left side search antenna and the right side search antenna, you can just rotate this forward searching vector to the left side and the right side with the same angle, which is this search angle. So we can create 2 rotation matrix, one for the left side and one for the right side. I'm gonna start by creating a matrix ident and then rotate this matrix using an angle at using a z-axis like this, and rotate the forward velocity to create the left side antenna velocity. So FL multiplied by this matrix. Now let's create another matrix for the rotating to the right side. So I'm going to copy this one and just replace the angle with the negative value. And let's name this matrix to 2, matrix 2, and name the new vector value as RVEL, meaning as a right velocity. Now that I have the vector value for the sensing direction, we can now choose the sensing point for each point. So let's say this is the point we're looking at. We want to create the vector, we want to determine the position of the sensor, 3 sensors, front, left and right. And you can get that by calculating the adding the current position plus the FL for the front side sensor position, for the left side sensor position we can say position plus LVEL, for the right side one, position plus RVEL. Alright. Now this is the important part. From that point that we have placed the sensors, we need to retrieve the pheromone information from the volume. Okay, so to get the volume from the positions, we can use the volume sample. Okay, and it's currently from the first input, and the name of the density is pheromone, and at FPOS, LPOS, and RPOS. So we need to calculate 3 different sensor values. So float FPH, let's call the front pheromone as FPH, and we need to do the same thing for the left and right. So LPH and right PH. and using the L position and the right position. Okay, now now that we have the pheromone, we could check the sizes between them. We can compare those sizes and determine which direction should this should each particle be turned to the left side or to the right side. And we can check the rule here for the comparison here, right here. So let's try to create this condition based on this sketch. So let's start from this one, turn randomly. So if the left side is bigger than the center and the right side is also bigger than the center, then we want to turn the angle randomly. So if RPH is bigger than forward PH and LPH is larger than FPH, then we need random turns. Else, if the right side or if the left side is bigger than FPH and the center FPH is bigger than the right side pheromone, then do the turn left. Else, if LPH is bigger than FPH and FPH is bigger than LPH, then turn right. Else, just no turn. So I just leave it as it is for this rule. Okay, so to turn the direction, we can create another matrix, a rotational matrix, in order to control the rotation. Okay, so let's do that. Alright, now inside this if conditions, I can calculate the angle, I guess. So let's start by angle 0, rotation angle 0. Did I get it somewhere? Oh, yeah, I need to rename this something different. So turn angle is 0. Okay, now if this is random, if the left hand and right side is bigger than the center, then you want to choose either left side or right side, which means minus rotation angle or plus rotation angle. So target angle is, first of all, use random values with some constant seed. Then check whether this is smaller than 0.5 or larger than 0.5, and if it's smaller, then use negative rank. If it's bigger than 0.5, then use positive rank. Okay. Now, if the left hand side sensor is bigger and the center is bigger than the right side, then the target angle will be a positive rank, since the rotation is the positive rotation means it's counterclockwise rotation. Else, if you want to turn it on the right side, then minus rank rotation angle. Okay, now that I have an angle, we can create a matrix for the turn. So Tmat is equal to ident rotate Tmat with this angle tang, and same as before, using up vector, y directional vector as a axis. Okay, now we can update the velocity, which is currently, the current velocity is is this one, right? So we can create a new velocity like tval derived from the velocity and rotate this using tmat. Okay, now the new velocity has been made. We can create a new position for the point. So let's say tpos is equal to the current position plus tval, and we might also want to normalize this tval and multiply it by a moving distance, which is this one, mdist. Okay. Apply, and that should be good. Now let's see what happens here, if the point does move or not, even if it's inside a volume wrangle. Oh no, I forgot to set the point attribute. Okay, so last of all I need to set the point attribute to update the point position. So set point attrib 0p at id. So this is the key point here. I'm using this id derived from the volume indexes and with the new position. Let's see if this works. Okay, let's go back. If I play it, yep, does seem to move, so it looks okay. What I need to do now is to set the boundary conditions here. So if the point goes outside the boundary, I want to go from the other side. Okay, so need that as a last touch for the point movement, which I can do it somewhere around here, I guess. Okay, and check the boundary size. So if the tpos.x is larger than this boundary box's max x, so max x, I can set the position for the x to be min.x. Pretty much the same for everything else. Tpos z is max z, then tpos z is equal to min z, right? So if the tpos.x is less than min.x, then coming out from the right side, tpos.x is max.x. Do the same for the z. If tpos.z is less than max.z, max.z, oh no, wait a minute, less than min.z, then tpos.z is equal to max.z. Now, simple enough. Let's see what happens. And all the points should stay inside the plane. Now that's good. Now currently there are no pheromone on the on top of the volume, inside the volume, so nothing will happen. It just goes straight for every point. So next thing we need to do is to update the density value using the point positions. So that is equivalent to this deposit step. Okay, so for each point I want to deposit some kind of pheromone on top of the trail map, in this case volume. So let's do that, and that's kind of a reason why I'm using volume wrangle to calculate everything, to access to the volume attribute directly using coding. Okay, so let's do this. In order to do that, maybe I might want to set some deposit size for this to determine, so that I'm not placing on just a single point but using a search radius, deposit radius instead. Okay, so I might need to go back to the init. Maybe I can do the search radius as well, set the search radius as well. Let's say the search radius, I'm currently using UV samples, so for that it might be okay to just use single point. And for the deposit size, maybe, well, yeah, I don't need the deposit size actually, but what I need to do, what I need to make sure is that okay, so I mean, this is the part where I'm controlling the point inside this if conditions. And the one that I'm going to write later is an independent code in order to update the pheromone based on the closest points. So from now on, I'm going to look at each voxel, and for each voxel I'm going to search for the closest points to that voxel. So there might be a multiple number of points there, and from all those points I would like those points to deposit some kind of pheromone on top of the volume to raise up the density. Okay, so for each voxel I'm going to search for the nearest points. So npts new points, looking for the particle at the current voxel position. And I also want to set the search distance, and since the single voxel size is equal to 1, I'll just say 1. So within the radius of 1, I'm going to get all the point values. I could also say like square root 2, because that's the exact exact radius of single voxel calculated from the center of the voxel. But I'll just leave this as this is. You might want to parameterize this as well to see the changes as well, maybe. Now after I got all the points, closest points for each voxel, I can loop through and just add up the pheromone into the current current velocities voxel. Access to the point number, then f at. We also need to get the pheromone deposit value, so So I guess I didn't need to get this here, but instead I need to get the D amount or deposit amount here from npt. Okay, and update the pheromone, increment the pheromone, spell mistake, pheromone with the amount. Okay, should be npts. Now I start to see some changes already. Okay, so let's see. And to make it a bit more exact, I could change the value of the pheromone based on the point distance to from the center, I think. So let's also try to do that. So let's also calculate the point position for the nearest point. And say calculate the distance to the current voxel point to the nearest point position, and we know that this is the maximum search distance for the nearest point. Maybe I can parameterize this near search distance. Okay, I guess dist, and let's set it to 1 for now. And based on it, I can change this distance value using fit, which is in between 0 to ns dist, to 1.0, which if it's the point is on the center, then that's the maximum. If it's outside the center, we can say like 0. 0 might be too radical. And finally, I can multiply the amount by dist, like this. Might do a good job here. Okay, now looks good for now. And the deposit part is done now. Let's see what happens at this point. Going to leave the loop and see what happens by playing. And I start to see some patterns already, with some particles moving, some kind of creating some kind of interesting path here. Now the problem is it's going wide and wide and wide, and that is because the value has been incremented more and more and more. So we also need another steps, and the one that I see here is not that smooth. So we need 2 more steps to go. One is to make it smoother by using diffuse, this like blur like effect here, and also the decay to make the pheromone value faded away by time. So I'm going to create another volume angle to do that after we have placed the deposit. I mean, I guess I could do the same stuff in one volume wrangle, and it might also work. Shall we try that? Yeah, we could try that. I mean, that way we could make the calculation faster, I guess. Let's try to do this in one volume wrangle, and if it didn't work, I'm going to separate it. Okay, so first of all, going to create but maybe not, maybe it doesn't work. Yeah, I don't think it works, because I need to recreate the pheromone value, I think. Yeah, let's do this on different volume angle. So that is diffuse and decay. Okay, first of all, so in order to calculate the diffusion for 3x3 means, which I think is explained somewhere right here, 3x3 means filter, it's pretty simple. You just need to get all the values, neighbor values, and just get the average. So that is equivalent to the mean value. So to get the neighbor fit, we can use 3 for loops starting from I equals to -1 to +1 incremented by 1, and copy this part, change the variable to n, paste it one more time. So we have 3 in a loop, and everything, those 3 loops will be used for x, y, and z for the volume to check the neighbors. Now actually we are dealing with the 2D volumes, so we don't actually need the third one, but just in case if you want to expand it for the 3D. Okay, so the current, first of all I'm going to get the current ID inside this loop. So int x is equal, this is the ix is the current voxel ID, and in order to get the left side or right side, you can just add by I. So if I was negative, then you get the left hand side voxel index. If I was equal to 1, then you get the right hand side voxel index. If I is 0, then you get the center, which is similar, which is equal to this ix. Okay, do the same for the y. I at y plus n, z iz plus t. Okay, and we also have to calculate the limitation, because if we are looking at the voxel on the left, far left, the left hand side, there's nothing here, so we need to check if this is within the voxel. Okay, so if x is larger than 0 and x is less than res x, and y is larger than 0 and y is less than res x, res y, and z is larger than 0 and z is less than res z, then we can calculate we can get the volume value from the neighbors. So first of all, create the index using those x, y, and z, x, y, z, and using this index we can retrieve the value from the volume. Let's name this tval, is equal volume index from a pheromone density with this index value. Okay, now let's also create the global variable like val starting from 0 and add this tval to this value. Now we also need to count up how many times we have retrieved the value, so that later on we need to calculate the smoothness, I mean the average. So I'm going to create the count number starting from 0, and each time we have added the value into this variable val, I'm going to count up, and after leaving the loop we can divide this value by count to calculate the average value. And this average value is going to be the mean value of 3 by 3 mean value. And I'm going to use that as a pheromone for a new pheromone value. Okay, you see that the value has been blurred a bit. Without this one, you have a bit more crisp image. If you have done this one, you have more smoothened value here. Now the final step is to apply a decay, which is fading this pheromone by frame with a constant value here. Now for that you can go back to the node controller and use this decay factor here. So this number could be any value. Let's start by 0.1. Might be too big, but let's see. Copy. And I'm going to just subtract the current value with the decay value here. And it might also be interesting if you change the decay value depending on the position as well, but for now I'm just going to use the global value here. So decay, and paste it right here. Alright. Okay, now I think everything is ready for the setup. It's time to visualize this. But currently, as you can see, it's a bit hard to see. Maybe the decay is a bit too high. Let's set it to 2.01 as well. Okay, now slowly I'm seeing some smoking value here. It's a bit hard to see what's going on here. It doesn't really create a trail here. Maybe if I should create a more deposit amount. Now it's too light. Also, controlling the gradation of this pheromone is a bit hard. So to make it a bit more simple, I'm going to retrieve the minimum and maximum volume values from the volume and use that to draw some gradational volume using volume visualize. So volume visualize, and first of all there's also a point here which you might not want to show, so first thing I would like to do is to remove those points. Now you can use delete to delete the points with the particle group, but I don't do that because somehow delete node or blast node takes a lot of CPU time to calculate. I'm not sure why. So instead I'm going to just use point wrangle, which makes it faster when removing the points. Same for switching. Switching seems to use a lot of calculation time, so these days I tend to use wrangle instead of switch, delete, or blast. Okay, so remove particles, and the particles that I want to remove is these one, and remove point DT node. Okay, it's not deleting. I think it's showing the cache here. Now it's deleted. Now let's connect this to a volume visualization node. And first thing I'm going to do is to make this ramp like this. Okay, and I'm going to use this gradation to control the density. And I'm just going to say asterisk. Now I think you can now change those gradation like this. Now let's also make the material. It's fine now. Now the range of this pheromone is currently set as 0 to 1, somewhere right here. Okay, right here. So click this one, and in order to make this to always go from black to yellow in this case, or orange, you need to set the minimum volume value here and maximum volume density here, which in this case a pheromone. To get that from the current volume, you can use the expression called volume min for the minimum, and I'm just going to retrieve the current node and prim ID is just 0. Okay, let's check. Yeah, the value has been retrieved, so copy this one to here and let's rename this to max. Okay, now everything is set, and if I play it, something should happen and start to show some calculation result. It should start to show some trails here. Now I think currently the resolution is a bit too low. It's 200 by 200, so let's raise this up to a bit more higher value. This one. Let's also raise up this particle to 500,000 just to see if this runs okay. Now, yeah, it does show some result here. It's a bit, it might be a bit too orangish currently, so if I increase the decay factor, let's see what happens. Well, since I'm using the minimum maximum as it is, the decay factor doesn't really change its result. So what I could do here is to change those deposit amount and the move distance, rotation angle, search distance, and so on, and see the differences. Okay, now let's see, what if I change this to 1? Does it change anything? Not much, not much. Okay, what if I set this rotation angle to 10 and search distance to 5? Okay, now it did something, but it's not really, doesn't really look good. Alright, set it to 2. Okay, still not that interesting, is it? I'll set it to 10. I'm not sure if I'm seeing the right result here. I might be missing some of the calculation. Let me also show up the particles, how it's been moving. Okay. Let's see. Now let's go back and see if I have implemented the values correctly. So for the calculation, I'm adding the pheromone, the amount here. Now this fit distance might be doing something wrong here. What if I disable this? Let's see what happens here. Maybe the search distance is not. Okay, now it's not that different, is it? Okay, what if I set this to 5 and 10 and 1? Switch distance, switch angle. Okay, okay, I realized one thing. I used the rotation angle with those search angle and a rotation angle, but I realized that I need to change this to radians instead of the degrees. Forgot to do that. So go back to the init and change this to radians. Okay, that's pretty necessary. And also let's try to make this function back, and let's have this distance, search distance value as a parameter here being promoted to the node controller. So going back and name this since this is a global one, near point, near search dist, near search dist. And set the range from 0 to say 5. Okay, and set it to 1 for now. Copy, go back, paste it right here. Alright. I think it's going to give something better result. Yeah, starting to see some pattern here. Interesting. Now let's try to change some of those kind of parameters here. Let's set search distance to 2 to see the difference. Alright. See some grid-like pattern here. What if I change the move distance to a bit faster? What happens? Not much changes, I guess. If I set it to 0.5, search distance to 3. Alright. What if it's like this? Okay, let me also change this to white, black and white. Might be able to see better. Okay, now let's also change the distance, moving distance to 3 and search distance to 1. See what happens. Now it shows more grid-like patterns, which is interesting. Yeah. What if I do it as 10? Okay, now I start to see some weird pattern here. What if I set the search distance to 10 and move distance to 1? Okay. Start to see more like a net-like network. Now if I change the search distance, search angle like 45 and rotation angle 30, what would happen? Yeah, start to see more clear images. Okay, getting more interesting so far. And at some point the image has been reached to the equilibrium. Let's try to change this decay, not the decay factor, but this near search distance to something different, like 3. Let's see what happens. Okay, not much difference, I guess. What if I set it to 0.1? So it gives you a bit more rough image, but the total result, the final result seems similar. So I guess keeping it 1 is... what if I set it to 10? Can I try this out? It might consist a lot of calculations because it's looking for all the points within the radius of 10, so might be a bit too slow. Let's set it to 4. Reset it. Well, I guess the result that I get is pretty similar to even if I set the radius to 1, so keeping the radius 1 is just makes sense in terms of the calculation speed. Yeah, it's pretty decent fast. Now let's also change these values like search angle to 50 and rotation angle to 45, and let's see what happens, which doesn't seem natural for the organisms to move. Okay. If I set it to 5 and set this to 60. Now it becomes more blurry, pretty blur. 10, 5. seems to create more small patterns. We set it 45 and 45. Okay, interesting. 75. Guess I need to go back. Much smaller. Yeah, still like it. Still like it if I move faster. Creates much smaller one. Much smaller one. Alright, so the basic setup has been created, and the result that I get is pretty satisfying from my perspective. At least for me, I'm really satisfied with the result. Okay, now the next step I could do, if you have more time to come up with me, I could randomize some of the values or differentiate some of the values to see some different, to create some constraints to this. And I haven't tried this myself yet, so I'm not sure what gonna happen, right? So keep that in mind. And one thing I could do, let's say, let's try to randomize some value here. Maybe using a noise function for some of the value here. Let's say, what if I change this search angle, multiply by noise p. And set the search angle to really big values like 180 degrees. Maybe that's too big, 90 degrees. And for the rotation, let's keep it to 50. So just give you a bit blurry image. Maybe not that interesting. Let me see. Let's go. Maybe I could create some constraints on the world, the global itself, instead of applying these values, changing these values. And based on the constraints inside the global map, maybe I could change some of the values here. So let's keep this to 30 for now. I want to make this values patterns a bit bigger. How do I do that? Okay, good enough. So let's try to create some constraint geometry to react with this geometry. I am just going to create a sphere, the circle, center on this plane, make it as a polygon, close this line, set it on XZ plane. The size is a bit too small, so let's keep the radius similar to this resolution. So copy this resolutions, set it as a uniform scale. Now that's obviously too big. And then multiply this by 0.25, 0.2. Okay, that should be a good size. Now connect this to the second input of this for loop, the solver. Let's try to read this value to change some of the particles movement or value here. Okay, so the circle coming from this one, Yeah. Now, for each points, we could search for the distance. We could calculate the distance with the constraint circle. So C dist is equal to XYZ dist from the second input with the current point position. And based on that, if C dist is less than 0.01, meaning if the point is inside the sphere, I mean the circle, I can change some of the value here. So let's bring this right before the distance estimation. Let's try to change some of the value here. What I could do, let's try to multiply this search angle by 2, also the rotation angle by 2. See what happens. Okay, I'm still seeing this cache here. Alright, let's see what happens. Play. And do I see any changes? Not really. Do I? No. I don't think so. So, oh yeah. What? I think I did something wrong here. I cannot use this P, but I should use this pos instead for the particle position. Okay, let's see this again. Oh yeah, now I see something really interesting right here. Alright. Okay. Now let's see what other parameters do. So if I change the move distance multiplied by 2, what happens then? Alright, now seems like I made a hole to this pattern, which is interesting. What if I multiply by 0.5? Alright. Okay. It stands out from the other network somehow. Looks like there is some nest here. Interesting. But I would like to keep it as 1. Now let's try other ones. What else? S distance, search distance. So search distance multiplied by 2 and see what happens. Alright, a bit more blurred network here. Interesting. But I'll keep it as 1. What else? Velocity is not the one that I can change. So it's pretty much inside here. There's also one that I can change for the D amount here, which might also be interesting to control the amount for each point. I'm not sure if that's going to change anything, but let's try. Let's see what happens. So the amount that I'm calculating here is around here, so I'm going to retrieve the distance. Float C dist is XYZ dist, second input. Current position is npos. Right, and if the C dist is smaller than 0.01, then I also need to bring this some beforehand. Then I would like to multiply this by, say, 2. See what happens. Now I'm not sure if anything has changed here. Let's try to make the value for the angle and angle for the search and the rotation to be 1 to see the difference Is there any changes? Not so much, I guess. Am I doing the right calculations? Let me check. For distance, C distance is XYZ this and pause, so yeah, I should be correct. What if I say 0? Well, one thing I missed, I have to say multiply equal. Okay, let's do this again. Well, it's already showing some differences. It's just brighter, makes it brighter. And I guess that's it. Yeah, not much difference other than that. So if I set it to 0.5, then I guess it's going to make it darker, I guess. Yeah. Something like a decal. Oh well, not that interesting, I guess. Maybe if you calculate the gradational distance between this from the center to the edge, maybe you can make a bit more interesting result. But I'm gonna leave this as it is. Okay, and I don't need this calculation. Right, so since these parameters changes a bit of patterns based on the constraints, I'm going to parameterize these as well for the multiplication value. So CHF S and C constraint, sign constraint, mult constraint factor. Okay, so I'm going to copy this one, paste it for all 4 of those parameters, and rename this dist and dist. Okay, promote this. Alright, so keep it as 1 for initial value, and I'm going to promote these all 4 into a null controller. So going back, bring this, and for bit linking, right. I might want to rename this search and constraint factor. Search and constraint factor. Rotate and constraint factor. Rotate and constraint factor. Search dist constraint factor, search dist constraint factor, move dist constraint factor, move dist constraint factor. Okay, all right, and let's also set the for now this is okay inside the subsolver, and go back to the null controller and set the range for these from 0 to say 3 to make it interesting. Alright, now we can test it out by moving this value. Gradually changes. Gives you some different result here with the different parameters here on real time. Well, that is a bit unexpected. Maybe I should set it as 1. Okay, let's do this again. Maybe I should increase the search, but rotate, try to decrease. See how it goes. Maybe for the search distance and the move distance, keep it as 1. Looks really blurry now. Right, still look blurry. Maybe I should make the rotation angle equal to 1. And set the search distance to 2. Now I realized that the calculations got a bit slower. I guess that's because I'm using XYZ distance calculation. That might be reducing the time. Well, I guess I like this result better. Now, let's look at the performance and see where it's taking time. Well, obviously, for the calculation node, yeah, it's for sure. And if I go back for the calculation, and I assume that these XYZ distance calculations are taking time, more time than the previous one. So if I disable this, I guess it should calculate a bit more faster. What? Anything else? Nope, that's the same. Yeah, so this is a bit more faster, but if you want to have a constraint, you need to have the calculations got more expensive. So it's up to you if you want to use this or not, I guess. Maybe you can have a condition if CHI use constraint to update those values. I mean, there might be a better way other than using XYZ distance to see if the point is inside a constraint or not. I just use this one as a close. I mean, the quick prototyping. There might be a better way. Okay, so I can use this use constraint to check, to switch between whether if I want to use the constraint or not. So let's give a toggle for the global. Use constraint. Alright, and apply, accept, and copy this one. Copy parameter, and move back to the use constraint here. Right, so now, right now the constraint is off, so you see a pattern if I click yes. The center point slowly fades to a bigger pattern. Maybe it's better to start off. Oops, I checked off somehow. Okay, so now you see the bigger pattern. If I multiply this, and the calculation is a bit slower than before. If I set these to 3 by 3, I should be able to get much bigger size. Maybe not. Maybe not. You gotta find out. Please find out yourself how these works together. Now changing those. well, at least I'm pretty satisfied with the result, so I hope you find something new here, and would like to end the tutorial somewhere around here. Can I just try one more thing and I'll finish this one. You can leave it anytime. Okay, so move distance is equal to, I'll just keep this as 20. Okay, so instead of using circle, I want to use something more characteristic. What if I use like a rubber toy? Where is it? I think it's a bit too small. So I can copy this resolution here and paste it to this uniform scale. Now it's really big. I want to rotate this. Not to this direction, not to that direction. Yep, but negative. Okay, and let's make this smaller, a bit smaller, 0.5, a bit more smaller, like 0.4 or 0.3. Maybe 0.435. Alright, now I want to use this as a silhouette to change the pattern. Now let's create the silhouette of this character. What did I do that? I think there's a way to do that. Was it divide? It's not sure. Dual? Nope. I think there's some node to create a silhouette, but well, I'm just gonna make it simple. Since I just need a closest point position, I'm just going to make this flatten by setting the Y to 0. Alright, makes sense. Now let's connect this instead of the circle and go back to the volume. Let's see what happens. Alrighty, that's a bit hard to see what it is. Does it? What if I make this a bit more high res? Like 1000. In this case, the point might be too much. I mean, currently the limitation is 500,000, so I guess that's fine. Okay, so slowly I get the result. It doesn't really look like a rubber toy, but I'll just say it's fine. And let's also limit the number of points to see if I can make it faster, make the calculation faster. A little bit. And the result I'm getting is pretty much the same, so I guess it's not much a problem by raising up the value here. Let me check if the value is really being limited. Yeah. But if I reduce to 100,000, does this still work? I'm start to see a bit the pattern a bit low res now, so you might want to keep the number of points at some range. Maybe 200,000 is a good point. Alright, but overall, the result that I get, I'm pretty satisfied. If I set it 300, you get more larger patterns. Okay, so that's it. That's it for this tutorial, and thank you very much for watching. Any comment is welcome. If it's positive, I would love it, obviously. Well, you can download the file from the video description of this project anytime and try to see how it's being implemented by looking at the file code. Okay, so if you like the video, please press like button and do subscribe. If you would like to follow other videos. I'm also doing the basic tutorial for the Vex called as Vex for Algorithmic Design, uploading every Friday or Saturday. And also I have also started Patreon myself. For anyone who would like to support me continuing creating these kind of videos, I'll be really appreciated if you could support me. Okay, so that's it, and thank you, and I'll see you in next videos. Bye.